Good afternoon, everyone. My report is on the field trial of the frequency dissemination system for Square Kilometre Array radio telescope. What is SKA? SKA is the radio telescope array now built in South Africa and Australia. The total collection area will be larger than 1 square kilometer, so that's what its name. This is a picture of the SKA Phase 1 in South Africa, and this is a zoom-in picture, and this is the central region. SKA's time and frequency system can be divided into 3 parts. One is the clock in symbols. The other part is the frequency transmission system. And the third part is the time synchronization system. These 3 parts, they are combined and work together. We worked on the frequency transmission system, and the equipment was packed in China, then sent to South Africa. This is the transmitter of the frequency dissemination system. It can support 10 channels, which can support 10 receivers in 10 different places. And this is the frequency receiver. It can automatically measure and compensate the phase fluctuation of the fiber link. So this test was carried out at the SK site in South Africa. The SK site was here in Losberg, and the Convolution is the SK support base, and the Carnival is a small town nearby. For this test, we have 3 main aims. One is test the performance of the frequency dissemination system working on the overhead fiber. For SKA, all overhead fiber can reduce the cost of the construction. And the second, we test the topological specifications of the frequency dissemination system. As I have said, in South Africa, there may be only 1 central station, and it will have hydrometer in symbols, but it will have thousands of telescopes. So the frequency dissemination system should be robust and can support the branching network to thousands of telescopes. Third, test the frequency dissemination stability and reliability of the relay system. For the antenna, some antennas may be 1,000 kilometers away from the central station, so we need the relay system. And as the time is limited, we will only describe this one in detail. The relay system was carried out between Convolution and Losberg, this station and here. The synthesizer was used as a clock signal. It output 100 megahertz. Then the signal was fed to the transmitter. It transmitted to the Losberg, recover it, and then use the signal again to the another system. Then transferred back to Convolution. We compared the phase, and the total fiber length is 153 kilometers. This is the equipment set up in Convolution, and this is in Losberg. They are placed in a steel container for prevent the RF emission. This is it's not very clear. This is the environment during the test. The test lasts about more than 4 days, and the blue line is the temperature fluctuation during test. In 1 day, the fluctuation is about 15 degrees, and in some days, the red and the green line means the wind gust and the wind strong, and the wind may be beyond the SK operation requirement. This is the test result. The trials proves that the frequency dissemination system can support the SK Phase 1 requirements, not the whole SK. For what? Because during this test, we also find a problem of our system. There is a bump in the Allen deviation spectrum, especially between averaging time 10 seconds to 100 seconds. Where does it come from? We are wondering. We try to find it from our system. This is a basic diagram of our system. This is the transmitter, and this is the receiver. For the transmitter, this signal V0 is the clock signal we want to disseminate. It can be expressed like this. But in local oscillator, but in the receiver, it also has its own local oscillator. It can generate a signal as we want. The signal from the clock assembly will transmit it through the fiber link to the receiver, but the signal generated by the receiver itself will double pass the fiber link and then turn back. It can be demodulated and it will be recorded as V3. We mix the V2 and V3, we can get signal V4. And we mix the V1 and V4 again, we can get the error signal V5. In signal V5, this phi 0 means the phase of the source. Phi p means the 2 GHz signal single pass the fiber link. The phi 1 means the phase of the local oscillator, and the phi p prime means the 1 GHz signal that double pass the fiber link. Ideally, it will be the same. The phi p prime and phi p will be the same. So this equation can be like this. This means phi 0 and phi 1, they are phase locked. But this is an ideal equation, ideal situation. In fact, mostly the mixture will have the nonlinear effect, especially the two inputs have certain relationships, such as one frequency is 2 times to another. In this situation, the signal V5 should be like this. The first term is the term we needed, but the second term and the third term are the leaking and maybe the harmonic term. So in this situation, the phase fluctuation of the fiber link cannot be totally compensated. It will be changing by the temperature. So if we want to improve our thinking, we put our 50 kilometer fiber into a temperature controlled box. The temperature fluctuation from 10 degrees in one day to 40 degrees in one day. And this still reacts. You can see for larger fluctuations, it will have a bigger bump. And what's more important is that for larger fluctuations, the bounce position was also moved to shorter averaging time. Then we come to the equations again. The bounce position, we can see it is equal to the time needed for the fiber link to obtain the phase fluctuation from one period to another. So as the phi p can be expressed like this, so we can get the time steps which can make the system phase fluctuation change from one period to another. Then it's equal, the bounce position equal to the time needed for the fiber link to obtain delta t equal to 0.072. It means if the temperature of the fiber link changes to 0.72, it will change its phase. This table is the calculation result from our the last slide. You can see for 10 degree temperature fluctuation in one day, it will cost about 300, and for 40 degree, it's about 80 seconds. And it matched very well with the experiment. So we confirmed that the bump was come from the nonlinear effect. Then how to remove it? We slightly changed our scheme by adding two different signals, not the same signals for 1 GHz. They are 1 GHz plus 100 Hz and 1 GHz minus 100 Hz. The others are still the same. In this situation, the error signal V5 should be expressed like this. The first term is still the same, but the second term and the third term, there contains the frequency offset, which they can be easily removed by a low-pass filter. In fact, this frequency is not exactly 1 gigahertz, so the fiber length composition is not ideally, but it's very, very small. It's just 10 power minus 7. In this case, we tested our new scheme in the temperature controlled chamber, and the green line is the result of the system. System was tested in the level of 15 degrees, change in 1 hour, not in 1 day. It shows a very good result. It proves that this system can fully satisfy SKA's requirement. That's all. Thanks for everyone.